Hello students, today we are going to take up the topic group 17 elements that are called halogens under P block elements in organic chemistry, chapter number 7. So let us start this topic with a very good thought. Don't let what you cannot do interfere with what you can do. I mean to say that sometimes we start thinking about what we cannot do. So due to that, we are not able to focus on the things, on the qualities within us, which can help us to do more things. So therefore, our performance decreases as we start focusing on what we cannot do. So try to focus on what you can do. So learning outcomes from this session is, so you will be able to explain about introduction, about the elements, the atomic size, the occurrence, reactivity, the electronic configuration, oxidation states, trends in physical properties, chemical properties with hydrogen, halogen, oxygen, and HYDRIDES. So let us start this topic. So group 17 known as halogens. Halogens means salt forming. Salt, for example, let us say NaCl, ionic compound, NaBr, NaI, NaF. So these are salts. Salts formed from halogens. So halogens are salt forming. And mostly they are non-metals, but metallic character increases down the road. Mean to say that iodine is having tendency to lose electron. There are 7 valence electrons in the outermost shell and 1 electron short of completing the octet. Therefore, the oxidation state general is -1, apart from other oxidation states. So, fluorine is the most electronegative element of the periodic table. Please do remember. Fluorine is the most electronegative element of the periodic table, but it is not having the highest electron affinity. Highest electron affinity lies with fluorine. Okay. So more about halogens. So these are non-metal and very reactive, and the most reactive non-metal is fluorine and then halogen. And general electronic configuration is Ns2 and P5. And these elements are toxic, mean to say that if they are inhaled, like fluorine is inhaled, so it can prove fatal depending on the concentration. And most of these nonmetals are diatomic state it exists, like fluorine F2, fluorine Cl2, Br2, I2, and all are having low polar covalent bonds. They all form ions with a -1 charge. As you know that 7 valence electrons are there, they need to complete the octet by gaining electrons. Therefore, the oxidation state general is -1. So, apart from these properties, halogens are having large electron affinity. Electron affinity is the amount of energy released when an electron is added to isolated neutral gaseous atom to form negative ion. And electron affinity decreases down the group. Means to say that if I am comparing fluorine with iodine, the electron affinity for iodine is less, fluorine is more. But it does not mean that fluorine. If you talk of fluorine is electron affinity is, if I say more, then it is wrong. So chlorine is having more electron affinity. This is an exception, and why it is so? Because of the small atomic size of fluorine. The 7 valence electron, they repel the new electron which is coming. So therefore electron affinity decreases. Okay. So the most common oxidation state of halogens is -1, but it can exist in the state of +1, +3, +5 and +7 are also possible. Halogens are known as very good oxidizing agent. So as you know that halogens are having 7 valence electrons. And 7 valence electron, it needs to complete octet by gaining electron. If 1 electron is gained, that will undergo reduction, and a substance undergo reduction as oxidizing agent. Each halogen is the most electroactive element in its rows. So as you know that 7 rows are there. So 7 rows means 7 periods. In each period, if you see, the halogens are on the right hand side. Right hand side means atomic size is minimum. And as you know that if you move from left to right, So you are moving from electropositive to electronegative. So end of the period, last element is noble gas, and before that we are having halogens. So therefore they are known as most electronegative in each of the respective rows. In regard to occurrence in nature, they are very reactive, so therefore they are found in the combined state, where they are found in the oceans as well as rocks in the form of halides, oxides and iodides. How? Na3AlF6, that you might have studied in 10th class also. This is an ore of aluminium cryolite. And CaF2, calcium phosphate, and sodium chloride, magnesium chloride, CaCl2, NaBr, and KBr, MgBr2, NaIO3. In this formula, I have missed out fluorine. So please, you have to add here fluorine. In this Ca5, PO4 thrice, F is there. So that is known as fluoropatite. Okay, Ca5, PO4 bracket 3 and F is there. Okay. Now, in regard to the properties of halogens, fluorine, chlorine, bromine, iodine and acetylene. Acetylene is radioactive, and fluorine is a gas, chlorine is a gas, bromine is a liquid, iodine is a solid. So therefore the melting point will increase down the group. As you see from here, melting point and boiling point are increases down the group because they involve the weak forces, and weak forces means van der Waals forces, and you know that van der Waals forces directly push into surface area. So more the atomic size, more the forces, therefore the forces of interactions are maximum when you go down. So in that way melting point and boiling point increases down the group. Similarly, it also exists in the form of isotopes. Isotopes are having same chemical properties but different physical properties, and so therefore the chlorine is having two isotopes in the form of chlorine 35 and chlorine 37. Therefore, as per the availability of percentage in the earth crust, we are taking as 3:1, means chlorine 35 75% and chlorine 37 it is 25%. So in that says we can say that chlorine is having average atomic mass of 35.5. So next is regarding to electronic configuration. In fluorine, the electronic configuration, outer electronic configuration is 2s2 2p5. It means it belongs to second period, and 17th group. Similarly, third period is chlorine, fourth period bromine, and fifth iodine and acetylene in the sixth period. As you know, down the group atomic radius increases because of increase of number of shells. Density of the halogens increases down the group. As you know that forces are going to increase as we move down the group. Therefore, the density, the volume, the mass is increasing to higher extent as compared to volume. Therefore, density increases down the group. Melting point we already discussed in regard to what process. Now, general electronic configuration we have discussed: NS2, NP5, and fluorine, chlorine, bromine, iodine. So now earlier we discussed that oxidation states is -1 because it is having tendency to gain one electron. But apart from that, it can exhibit +1, +3, +5, +7. Why? So if you write the general electronic configuration of halogen NS2 NP5, and as you can see from here, there is one unpaired electron. So if this one electron is gained, so it will undergo -1 oxidation state, and if this electron is lost, then it will undergo +1 oxidation state. Similarly, if I excite these electrons, this one electron can jump to d orbital. So there are now having three partially filled orbitals and having one electron each. So if this electron is lost, so +1 oxidation state. If this is lost, +2, then this is lost, +3. So therefore we can say +3 oxidation state is possible. Similarly, if I will remove one more electron from here in the excited state, so now we are having 5 valence electron. So 5 unpaired electrons. 5 electrons can be lost, so therefore it will exist as +5 oxidation state. Similarly, if I will remove once more here, one electron from here, so that what will going to happen is, here also this electron will be there, 1 only, not 2. So there will be 7 valence unpaired electrons, so therefore oxidation states will be +7. So other properties in regard to the physical properties, decrease in the reactivity. It means fluorine is the most reactive in the halogens because of low bond association energy. Because there are repulsions between the valence, between the lone pairs of fluorine with another fluorine, therefore the bond energy is minimum. And as you go down the group, atomic radius increases. Why? Because of the increase in number of shells. And here the C, decrease in power to attract an electron to form negative ion. That is electron gain enthalpy. So electron gain enthalpy decreases down the group. But in special case you should remember that fluorine is having more electron affinity as compared to fluorine. Otherwise down the group tendency decreases. Increase in the melting point, boiling point we have discussed already because of multiple forces of attraction are maximum as towards when we move towards acetate. The color of the elements tends to get darker. So we will study more about the color also. So if I will see the color of fluorine is pale yellow and for chlorine is greenish yellow or yellowish green, and for bromine it is red and iodine it is violet or black. So why it is so? So if we see that these halogens can absorb light in the visible region like violet, indigo, blue, green, yellow, orange, red. Then these electrons, after absorbing energy, move to the excited state. They reach the higher energy levels. So as the size of the atom increases down the group, fluorine to iodine, and iodine needs lesser energy to shift the electron from lower energy shells to higher energy. So as we go down the group, the energy required to shift the electron from low energy to high energy progressively decreases down the group. Therefore, the fluorine being the smaller in size need more energy to shift the electron from low energy shell to high energy, or we can say it will absorb higher energy radiations. Higher energy radiations means low wavelength radiations. Low wavelength radiations means violet light. So we can say that fluorine molecules absorbs violet light. Therefore, it is showing the complementary color of yellow or pale yellow. While large atomic size of iodine, it needs less energy, so it absorbs only yellow wavelength light. So thereby yellow or green also, and thereby show the complementary color of violet or black. So that is why the color of halogens deepens down on moving down the group. This is a very important question which was asked in the board exams. Now come to the properties of halogens next. And you know that halogens are poor conductor of electricity because normally these are gases. Gases are always a poor conductor of electricity because there is no ionization taking place in that. Although iodine can form certain compounds which can conduct electricity, as such gas state it will be a poor conductor of electricity. Next is already we have discussed about this, that fluorine, chlorine are gases, bromine is a liquid, and iodine is a solid, and as well as astatine. And very reactive, will even react with glass. And if you see that fluorine, this is very reactive and it can even react with glass. And halogens are commonly found in diatomic molecule, gain an electron when reacted oxidation state -1. So this already we have discussed about the state, and reason also we discussed down the group van der Waals forces increases because of increase in atomic size. And this is about bond dissociation energy, and bond dissociation energy is, see, if you go down the group, bond dissociation energy will decrease. But here why? Because bond length will be more in case of iodine as compared to fluorine. But one important case you need to remember is fluorine is having the very less bond dissociation energy as compared to chlorine. Why? Because fluorine being small atomic size and the valence electron are 7. So 6 electrons are existing as lone pairs. So 3 lone pairs are there on each fluorine. So this lone pair repulsions are more in case of fluorine because of small atomic size. Therefore, the bond dissociation energy of fluorine is lesser as compared to that of chlorine. Please remember that. Next is activity series. So therefore, in this regard, fluorine is the most reactive halogen as compared to iodine will be the least reactivity, and down the group reactivity decreases in a halogens. And so this is just similar to the reactivity of metal. These are known as reactivity of non-metal. Reactivity of non-metals are different than metals and opposite also. Now comes to oxides. So oxide halogen can form oxide in the form of OF2, O2F2. OF2 is thermally stable at 298 Kelvin. These oxides are for fluorine, for chlorine, bromine. Now you can see from here is that fluorine OF2 in this case, oxygen is having positive oxidation state and fluorine is having negative oxidation states. And why it is so? Because of higher electronegativity of fluorine. So you cannot accept this F2O2. F2O2 will not be stable. So why? Because fluorine here is existing in the positive oxidation state, which is not possible. Fluorine being the maximum electronegative element in the periodic table, it cannot have a positive oxidation state. Please do remember that. Okay, so this is not practically possible. Similarly, higher members or the other members except fluorine, it can have positive oxidation states like +1, +3, +5, +7. So if you see here Cl2O3, this is showing the oxidation state of +3. Similarly Cl2, this is 4 +4. Similarly here +6, here +7. So this oxidation state can be shown. And next is plutonium to plutonium hexafluoride. What this means? Plutonium to plutonium hexafluoride means plutonium was initially at 0 oxidation state, and that oxidation state for plutonium in plutonium hexafluoride is +6. It means the oxidation state changes from 0 to 6. And who has done that? Fluorine. And therefore fluorine is very good oxidizing agent. Okay, fluorine is very good oxidizing agent. And if I talk of fluorine, chlorine, bromine, iodine, which will be the most reactive and best oxidizing agent is fluorine. Actually, oxidizing property depends on the reduction potential values. If you see the electrochemistry chapter, the values of reduction potential for fluorine is having +2.87 as against iodine of +0.62. So I want to say that reduction potential of fluorine is maximum in halogens. So therefore the best oxidizing agent, even though best oxidizing agent in the periodic table. Actually, reduction potential does not depend on only one factor. Reduction potential depends on 3 factors basically. Reduction potential depends on the ionization energy also. The reduction potential depends on the lattice energy also. And reduction potential depends on the electron affinity. Reduction potential depends on the hydration energy. Basically 3 parameters are deciding: electron affinity, bond dissociation energy and hydration. So these 3 factors collectively decides the electron reduction potential values. More is the electron reduction potential value, better will be the oxidizing agent. So this concept is also very important. So these are oxides of group 17 elements. So they can ask you about the oxidation states, or they can ask the question about to write the example of oxygen compound with halogen which is showing the specific oxidation state. So halides. Halides means to say that halogen is forming bond with another halogen, that are called interhalogens basically. And type of these interhalogens are XX, XX3, XX5, XX7. So here one X may be different from the another X about in the size or in the electronegativity. So now you see from XY the first example is ClF. So you cannot write FCl. So because fluorine is the most electronegative, so other elements apart from fluorine can exist positive oxidation state, but fluorine does not have the oxidation states of, it is having only -1 oxidation state, it's not having oxidation state of +1, +3, +5, +7. Okay, and similarly IF7 here, so here iodine can show the +7 oxidation states also. Now hydrides. Hydride means halogen combined with hydrogen. And if you see hydrogen combined with halogen will be HF, HCl, HBr, HI. Now the point is these are halogen acids. So this about the acidic strength the question can be asked. And as you know that HF, HCl, HBr, HI, the bond length will be maximum for HI. Therefore the breaking the bond will be easy. Therefore the reactivity or acidic character will be maximum for HI. And bond association energy, if you can see from table also, the bond association energy is maximum for HF, that is 574, and the minimum for HI, that is 295. And acidic character, you can see that acidic character is maximum for HI. So pKa value, more negative the pK value, higher is the acidic character. Next is about metal halides. Metal halides are ionic compounds basically. The bond formed between metal and non-metal. Non-metal are halogen here. So now we are talking of here the metal and the halogen, which is what about the ionic character? MCl, MBr, Mi. So now you know that more the electronegative difference, more ionic character will be there. In this case, let us say NaF, NaCl, NaBr, NaI. If these four examples are there with us, I will surely say that NaF is the most ionic. Why? The difference in electronegativity is deciding. Fluorine is the most electronegative and sodium is most electropositive. If sodium is same in all the cases, and then we can say that the NaF, that would be the most ionic. Similarly, for covalent compounds, if we see tin tetrachloride, PbCl4, SpCl5, you have 6. More the oxidation state, more the covalent character would be. And here also you can see that sodium is oxidized to NaCl, and who has oxidized? Chlorine. So chlorine is acting as oxidizing agent. So this concept of oxidizing agent and reducing agent should be very clear to you. So summary for this is group 17 of the periodic table consists of fluorine, chlorine, bromine, iodine and acetine. Different colors are there for that, and these elements are extremely reactive and found in the combined state only. The common oxidation state of element is -1, and however highest oxidation state can be for +7, basically for iodine. They show regular gradation in physical and chemical properties. Therefore oxides, hydrides and interhalogen compounds and oxo acids. Let us take up one or two questions. Halogens have maximum negative gain enthalpy in respective period of the periodic table time. Halogens, you know that as you move from left to right in a period, the atomic size decreasing, and therefore the nucleus having proton coming closer towards the valence electron. To complete the octet, the one electron is having the tendency, shortage is there. So effective nuclear charge will increase as we move from left to right. Therefore, the energy released when electron is added to neutral isolated gaseous atom will be more for halogens. So once they are accepting electron, they acquire the stable noble gas configuration, therefore getting the stability. So next question is, although electron gain enthalpy of fluorine is less negative as compared to chlorine, fluorine is stronger oxidizing agent than chlorine. Why? So this question is very important, as we told earlier also. It is due to low enthalpy of dissociation. Low enthalpy means breaking of the bond. So as you know that fluorine, chlorine, although the bond length is small, but the lone pair positions are maximum due to small atomic size. That's why low bond dissociation energy and high hydration enthalpy of fluorine. So you know that hydration energy depends on the charge density. So charge is the same for all halogens, but the density is different. So density will be maximum for fluorine because of small atomic size. That is the reason. So here this is we have discussed already. And question number 3, fluorine exhibit only -1 oxidation state, whereas other halogen exhibit +1, +3, +5 and +7 also. Explain. So fluorine is the most electronegative element and cannot exhibit any positive oxidation state. Other halogens have d orbital and therefore can expand their octets and show +1, +3, +5 and +7 oxidation state. I am hopeful that you are knowing these answers. So congratulations to you for that. So let us repeat the thought. Don't let what you cannot do interfere with what you can do. John Wooden. Thank you.